from our previous study of signal flow graph, we were to continue by looking at the example of a signal flow graph in order to see how to apply the Mason's gain rule or the Mason's gain formula in order to determine the transfer function of a system. And here is the first example that we are going to look at, and this is how it is. So this is a signal flow graph that has been given. So we are supposed to get the transfer function of this particular signal flow graph. So as we said that in this case we are not going to use the block diagram reduction method, but rather we are going to use the inspection method, and that is application of the Mason's gain formula in order to determine the transfer function. So the first thing that we are going to look at in this method is that we are supposed to identify the paths, all the forward paths. And just as a reminder, we did say that the forward paths are just paths that start from the input to the output, and it must traverse. It should not traverse a path more than once. So we are going to identify the forward path. So the first thing that we need to look at, we are going to look at the forward paths. We are going to look at the forward paths. So it has to start from the input and ends at the output without changing the direction of the arrow. So we can name the paths as P, so we can talk of path 1. So we are going to look at path 1. If we talk about that, then there is the input here. Then it can go through G2 to G4 to G6. So we can say our path 1 is going to be G2, G4, G6. Then we can look for another path, the corresponding path for that. We can talk of the path 2. So the second path, we can talk of G3. We can talk of G3. We can talk of G3. Then from G3, we can come to G5. Then we can go to G7. And of course, 1, which will not make any difference on that particular gain. Then we continue and look at all the paths. We can talk of the path 3, P3. So when we talk of the P3, we are now going to look at which other path can lead us to that from the I input to the output. We can talk of G2 coming to G1, then G7. So that can be another path. G2, G1, G2, G1, G7. That is another path that we can talk about. We can go ahead and look at the fourth path. The fourth path can be G3, G8, G6, G3, G8, G6. And we can look at another path, path P5. If you look at P5, we've said that the path should be from the input to output, and it should not traverse a path more than once. So we can have something like G, we can talk of G2. It starts with G2, then G2 goes to G1, then using the feedback minus H2, it goes to that point, then goes to G8, then finally to G6. So that one can also be a path. So we can talk of a path G1, not really G1, but G2. We talked of G2, G2, G1, G2, G1, then coming back, minus H2, can have H2 there, minus H2, G8, and finally G6. So that one is also another path. We can talk of the P6, the path number 6. Of course, that one should be a negative. So remember, this is a negative. So we can talk of P6, P6 here. We can talk of G3, P6, G3, G8, minus H1, G1, G7. So if you look at it, we have not changed the direction of any, and there is no node that is traversed more than once. That is traversed more than once. So the path has to traverse a node. It has to pass through a node once, and that is what we have maintained. So it is minus G3, G8, H1, so the minus here, cut us for minus H1, then you can have G1, then you can have G1, then from there we can have G7. So those ones are the paths. Maybe you can look at it further and check if there is a path, but so far so good. These ones are the paths that we can identify. So by inspection, you start by identifying the forward paths. So we have identified the forward paths. Then afterwards, we are going to look at the individual loops. So we are going to look at the second part. We need the second part. The second part of our inspection is going to be looking at the individual loops. So we are going to identify all the individual loops that are here in order to determine the transfer function. So the individual loops here, we can look at the loops. Looking at the loops, we can only see the explicit loops can be this and that, and maybe there is a loop that moves in between. Again, when we are talking of the loops also consist of paths, and again, there should be no node that should be traversed more than once, and therefore we can talk of the loops. We can call the loops L. Talk of L1. L1, we can talk of minus, so we can talk of this starting from that point, then goes G4, then minus H1. So we can talk of minus G4 H1 as one of the loops. We can talk of L2. L2, the second loop, we can talk of minus G5 H2. And maybe we can also have the third loop. The third loop is going to be, we talk of the third loop. Loop starts from anywhere, so as long as it is able to go back to where it started from. So we can have minus H1, coming to G1, coming to minus H2, and coming back to where it started from. And of course, because it involves the two negatives, it will become positive, and we can just write the product of the same. So it is going to be G1, G8, H1, H2. Can talk of G1, G8, H1, H2. So we have not necessarily followed it the way it is, but we've just ensure that all the products are inside. So we are talking of this loop. Starting, we've said that it can start from anywhere, but you don't change the direction of the arrows. That way, and there. So it stops at that point. So that is now what we refer to as the individual loops. Then the third analysis that we are going to look at is, do we have any combination of non-touching loops? We start for the individual loops, then we go to non-touching loops. So we are going to look at combination of non-touching loops. Then we get their product. Do we have non-touching loops? Of course, we only have three loops here. So we are going to look at, do this loop and that loop share a node? Or do this loop and this loop share a node? Therefore, we can talk of combination of two non-touching loops. Combination of two non-touching loops. Combination of two non-touching loops. So when you look at the combination of two non-touching loops, we are going to look at this loop and that loop. So we have G4 from this, we have G4 minus H1, and the other loop is G5 minus H2, and therefore both of them are negative, and we can see that they don't have they don't share a common node, and therefore we can talk of that one as non-touching loops. So the combination of two non-touching loops, we can talk of G4, G5, G4, G5, H1, H2. And that is now the combination of non-touching loops. So that is now what we have as far as the combination of non-touching loops are concerned. Looking at this and that, let's look at that loop and this loop to see whether they are non-touching. We have G4, of course, with the existence of H1 here and H1 there, it means that the loops share a common node. Looking at this loop and that loop, with the existence of H2 and H2 here, that one will signify. But you should always look at it from the signal flow graph itself, so that when you talk of that, and we know that the other loop was that way. So that one was the loop, and in that case, they share a common node, and therefore we only have a single combination of non-touching loops. And therefore, from that point, we should be able now to look at the various determinants of these particular paths. So we are going to look at the various determinants of these paths by looking at H2, by looking at P1. So we can talk of P1 and its respective determinants. So we look at this P1 and we look at all these loops, P1 vis-a-vis the loops, and therefore we look at which loop has P1 not touched. Then you come to, if you look at that, it has touched this loop. So we can look at G1, G4, G2, G4, G6, G2, G4, G6, and this first loop is G4, G1. So you can see that it has touched that loop, and therefore it means that it is touching that loop. Then we look at it vis-a-vis the other loop, minus G5, so it does not touch that loop. And therefore, the corresponding value of that will be 1 minus the loop that it doesn't touch, which is going to be into bracket G4, that is G5 minus G5, H2. Then that is going to give us 1 plus G5 H2. So that is the value for that particular determinant. Then we can look at the determinant for the second one. Again, we have G3, G8, G3, G5, G7. So looking at that again, this one, it touches G3, G4, G3, G5, G7, G3, G5, G7. It touches the loop G5, H2, but it does not touch the first loop. And therefore, it will be 1 minus into minus G4, H1. Of course, that is going to be 1 plus G4, H1. It's going to be the product, the determinant for that case. So in that case now, we have those determinants. All these, we are supposed to get their determinants. So we get for that third one. And then G2, we have G2, of course, it has touched that first loop there. G2, G1, it has touched the second loop, and therefore it is going to be 1. So if you look at that again, G3, that is a node for one of the loops, G8, that is another node for one of the loops, and then it has touched both the loops, and therefore that one is also going to be 1. And you will find that that 3 should be equals to that 4, is equals to that 5, is equals to the determinant for 6, which is equals to 1. Because if you look at the paths from part 3, part 4, part 5, and part 6, all of them touch all the loops, and therefore their determinant values will be 1. Then from there now, we are ready to come up with our transfer function. And from this, we can now obtain our transfer function. As, of course, now we have everything. So maybe we can get to the transfer function. Obtain the transfer function. So if you want to obtain the transfer function like this case now, we can talk of M will be given by P1 dot that 1 plus P2 dot that 2 plus P3 dot that 3 plus P4 with the respective determinant plus P5 with the respective determinants plus P6 with the respective determinant, and all this will be over the overall gradient. And the overall gradient will be, if we remember how we get the overall gradient, the overall determinant. The overall determinant will be given by 1 minus, it will be 1 minus the individual, the sum of the individual loops of which the sum of the individual loops will now be, it will be 1 minus into individual loops we have minus G4 H1 minus G5 H2, and that one is plus G1 G8 H1 H2 G1 G8 H1 H2, and that is now what we have, of which if you simplify it, then of course that negative sign is going to cancel the others, and therefore from there we are going to get, of course, there is that, that, and then plus the combination of non-touching loop, the combination of non-touching loop, which is G4, G5, G4, G5, H1, H2, of which if you simplify, then we are going to get our overall determinant. The overall determinant will be, now the overall determinant will be 1 plus G1 plus G4, 1 plus G4, H1 plus G5, H2 minus, of course that is going to change, minus G1, G8, H1, H2, G1, G8, H1, H2, and plus, of course, G4, G5, H1, H2, G4, G5, H1, H2. Then we can now get the values of the various determinants in order to get the value of M. So our M now, if you look at that from there, our M now is going to be given by the now all this that we have here, we combine them. Our M will be given by 1 now, P1 times the respective determinant, which is going to be G2, G4, G6 into bracket 1 plus 1, this one, 1 plus G5 H2, 1 plus G5 H2, close the bracket, plus G2 times the respective determinant, that is P2 times the respective determinant, that is G2, G3, G5, G7 into bracket 1 plus G4H1 plus, of course, all from that one is 1. They have the determinants is 1. So every part has got a determinant of 1 because they will be, from the analysis we realize that they touch all the loops. So from there we have, for that we have only G2, G1, G7 times 1, which will be G1, not really G1 but G2, G1, G7 times 1, of course no change, G3, G8, G6 times 1 again, plus, of course now it is minus G2, G1, H2, G2, G1, H2, G8, G6, G8, G6, again minus G3, G3, G8, G8, H1, G1, G7, H1, G1, G7, and then all this will have a denominator of that, which is now 1 plus G4, H1, plus G5, H2, minus G1, G8, H1, H2, G1, G8, H1, H2, plus G4, G5, H1, H2, G4, G5, H1, H2. And this is now what the transfer function will be as far as that particular system is concerned. So that is how to obtain the transfer function. All these are numerator, and that is the denominator. So you can see from there, from the analysis, we have that, the respective determinant, that, and of course from here, the determinants were found to be 1 from the inspection and analysis, and from that we are able to come up with that particular transfer function. So we can look at another example, example 2, whereby we have been given a signal flow graph and you've been asked, the question is, using the Mason's gain formula, find C over R of the signal flow graph shown below. So the signal flow graph is here. Of course, you can see the input, then we have G1, G2, G3, G4, and so on. So we want to look at the signal flow graph as far as the system is concerned. So the first thing that we look at is the analysis. Yes. So we are going to start by looking at the analysis, and just as we had said before, we are going to start by looking at the forward paths. We look at the forward paths. So what are the forward paths that are there? So from there, let's call them path 1 again. So what can we see? And we say that the forward paths, it must start from the input and it must end at the output without traversing a node more than once. And in that case, we can look at, of course, you can see that G9 will be a feedback and therefore it is going backwards. So we can talk of a path starting from R, then goes to the gain of 1, G1, G2, G3, and G4. So we can simply say that we have a path G1, G2, G3, and G4. So that is our first path. We can also talk about the second path. Our second path, whereby we can talk of a second path. So our second path here, because that is also feedback. G10 is a feedback. So our second path, in this case, we are going to have G1. We have G1, that one, G1. Then it comes to G5, G5, G8, G4. So that is our second part. So we talked of G1, G5, G8, and G4. So that is our forward path that we can talk about. I don't see any other path, and therefore that one takes us to the next part of analysis, and that is the individual loops. Individual loops. So we can look at the individual loops, and from the individual loops we can see there is the first loop. We can talk of G1, G1, G2, and it is coming back through G9. Therefore, we can talk of our L1 to be G1, G2, G9. So we can talk of G1, G2, G9. The second loop we can talk of, there is G3, G4, G10, L2. We have G3, G4, G10. We can talk of the third loop. We can see that there is a third loop, that is G1. There is G1, G5. We have G1, G5, G1, G5, G8, G4, G10, coming back to G9. So we can have a path G1, G5, G8. So we have a path G1, G1, G5, G5, G8, G8, up to that, G4, G4, then it is going back through G10, G10, then using G9 up to G1 where it started from. So that one can also be a path. Then we can also talk about L4, the next loop. The next loop can be G5. We have one that starts from G5, then goes to G6 and back to where it started from. So we have G5, G6. That one can also be a loop. And then we have a self loop. We can talk of a self loop, L5, as G7. G7 is now the self loop. So those ones are basically the individual loops that we have. Then we can now look at the combination of any two non-touching loops. So which loops are not sharing a node? So that is what we are going to look at. We can look at the loops that are not sharing a node and come up with a loop. We can see that the first loop, that is L1, and also the other loop that we can talk about, we can talk about two loops that don't share a node. So we can look at these loops like the loop, look at this loop and that loop. Do they share node L1 and L2? So we look at L1 and L2. So if we look at G1, G2, G9, G1, G2, G9, and G3, G4, of course, there is that. So they share. So if you look at that, you can find a loop that is the first loop. That is the first loop, and the fifth loop. They don't share. The first loop and the fifth loop, this and that don't share node. So you can talk of their product. So we can talk of combination of any two non-touching loops. Combination of any two non-touching loops. So you look at these loops. So you can see that this loop, we can look at all the loops together. G1, that one we've realized that it is, of course, there is G1 here. So there is something that they share. So then we have another loop, G1, G2. You have G1, G2, G9, and then we can talk of G5, G6. G5, G6, of course, they share a common one. Then we can have only that. So therefore, we can talk of the first non-touching loop can be G1, G2, G9, G7. So that is the first non-touching loop that we have. We can go to the second one. Maybe we can go to the second. We look for the second non-touching loop that we can see. We look at this loop and that. So G3, G3, G4, G10. G3, G4, G10. And we look at it versus vis-a-vis G1, G5, G1, G5. Of course, they have a common node somewhere. That is at G4. Then we look at that loop vis-a-vis this loop, G3, G4, G10, G3, G4, G10 versus G5, G6, G3, G4, G10 versus G5, G6. We realize that they have, we realize that they don't touch one another, and therefore we can have G3, G4, G10, G3, G4, G10, and G5, G6. And G3, G4, G10, and G5, G6. So those are the combinations. So we can talk of non-touching loops. Then the other one, we can look at another one. Now we have that and that. So what of this and this? That is G3, G4, G10, G3, G4, G10, and G7. Again, they don't have a common. So we can have G3, G4, G10, and G7. So that is another loop. And then we can look at this and that. That is G1. Now we are here. We can look at this loop and that loop. And then we look at finally the other loops. So G1, G5. So G1, G5, G8. If you look at G5, it is present here. So there is no need to look at it further. If you look at this and that, of course, at this point here, at that point here, this is going to be a common node for both because G7 is here and the other one starts from here in that manner. So in that case, that one means that the only combination of two non-touching loops that we have are 3. So we can find, we can call this one, we can have the 3 of them, and then from there we can now go to, now we have everything, not really, but we have to find the determinants for each. So let's look at the determinants for each. The first one, which loop does it not touch? This first path. If we look at this first path, it is here. It is touching that loop. It is touching that loop.
It is touching the loop that comes from here up to that. The only loop that it doesn't touch is the one for G7, and therefore that is going to be 1. It's going to be 1 minus G7 minus into G7, which is just going to be 1 minus G7. We go to the second one. The second, is there a loop that one does not touch? Is there a loop that it doesn't touch? So, looking at the second path, G1, G1, G2, G1, G5, it has touched that loop, it has touched that loop, and again it has come to that, it has touched that loop, and it has touched that loop at that point. And therefore, its determinant will be 1. Then we can now get the overall determinant. The overall determinant is given by 1 minus the sum of individual loops. The sum of individual loops in this case is going to be given by, the sum of individual loops is going to be given by 1 minus into G1, G2, G9, G1, G2, G9, plus G3, G4, G10, G3, G4, G10, plus, so we are here, G1, G5, G8, G4, G1, G5, G8, G4, G8, G4, G10, G9, then minus plus G5, G6, G5, G6 plus G7. So that is the first part. Then the combination of two non-touching loops plus the combination of two non-touching loops plus we can get the whole of that. Of course, there is nothing that is negative, so it's going to be plus G1 plus G1, G2, G9, G2, G9, G7 plus G3, G4, G10, G5, G6 plus G5, G4. Is it G5 or G3? It should be G3, G4, G3. So this one should be G3, G3, G4, G10, G3, G4, G10, G7, G10, G7. So that is now the overall determinant. Then from there now, we are ready to write our transfer function. So we can write our transfer function. We can now write our transfer function because we know that our M is going to be, we have two paths. The first path times its respective determinant plus the second path times its respective determinant all over the overall determinant, of which now, if we load that, then our M is going to be is going to be G1, G2, G3, G4, G1, G2, G3, G4 into 1 minus G7 plus G1, G5, G8, G4, G8, G4 times 1, which will not have any change. So we can have our M there going to be, then this one will be all over this, all over that 1 minus G1, G2, G9. So minus G1, G2, G9 minus G4, G3, G10, G4, G3, G10 minus G1, G5, G8, G1, G5, G8, G4, G10, G9, G4, G10, G9, minus G5, G6, G5, G6 minus G7, and then plus, of course, G1, G2, G9, G7, G1, G2, G9, G7. Then, of course, we look at G4, no, not really, G3, G4, plus G3, G4, G10, G5, G6, G5, G6, plus G3, G4, G3, G4, G10, G7. And of course, this one will be the numerator. You can expand it, but that one will not make any big difference. Then from here, you can get that. So this one is the denominator, while that one is the numerator. And you shall have obtained the transfer function by inspection or by the use of the Mason's gain formula. So that one is the second example. So I want, in our next tutorial, we are going to look at how are we going to change the block diagram to signal flow graph, and then use the signal flow graph in order to determine the transfer function of a system. So we are going to look at the block diagrams, how they are supposed to be changed to signal flow graphs. Then from that, you are going to use that particular signal flow graph in order to determine the transfer function. Remember, we said that the signal flow graph, it can always be used in order to determine the transfer function of a complicated block diagram, whereby now you will not be using the block diagram reduction rules in order to determine the transfer function. So we are going to look at how do we convert the block diagram into signal flow graph, and after that determine the transfer function of that particular signal flow graph that has been developed from the block diagram. So that is what we are going to do next.